We're starting section 16.3, conservative vector fields. First we do fundamental theorem for conservative vector fields. Then we do properties of conservative vector fields and how knowing that a field is conservative makes the computation much easier. And then there is a section that is applications in physics and is somewhat not mandatory. It's more optional. So from 16.1, we talked about that a vector field F is conservative if there exists a scalar potential, a function such that gradient of that scalar potential is equal to the vector field. So if you take the gradient of this scalar function and you get a vector field, then that vector field is a conservative vector field. If F is conservative on an open connected domain, then any two scalar potential of F only differ by a constant. Well, that sounds familiar. That's more like calculus of one variable story, that if you any two functions that are their difference is a constant, their derivative is going to be the same. And so an antiderivative of a function is a function, and it could be different by another antiderivative by a constant. Potential can be calculated by antidifferentiate by the antidifferentiate and match up the piece method. That's the one that we tried in 16.3. And if F is conservative, then curl of F is equal to 0. Some of these stories brings us to the fundamental theorem of multivariable of conservative vector fields. So assume that F is equal to the vector field F is equal to the gradient of scalar function F on a connected domain D. If R is a path along a curve C from point P to point Q in D, then the integral, the vector line integral over curve C of vector field F dot dr is equal to the potential function at one endpoint, evaluated at one endpoint, minus the potential function evaluated at the other point. What does this look like? Remember, from calculus of one variables, you go integral from A to B of basically f of x dx, for example, is going to be f, which is the antiderivative at a at b, minus f at a. Here the little f, which is the potential scalar potential function, acts like the antiderivative over here, basically. That's why it's called fundamental theorem of conservative vector fields. Now assume that f is equal to gradient of f, which f is the scalar potential on the domain D. If R is a path along a curve C from point P to Q, point Q in D, then the vector line integral of f dr is equal to f evaluated at Q minus f evaluated at P. So how do we go about proving this? First, let's start from the left-hand side and rewrite the information that we have. How do we compute the vector line integrals? We compute r prime of t, then we dot it with f evaluated at r of t, and then this goes from the two endpoints, which one is the t value that gives p, the other one is the t value that gives q. So I have to figure out what value here. A gives out point P. If I plug it into R, I get point P. B gives out point Q. Now, going about writing the left-hand side as the vector line integral, I end up with one thing is we're claiming that f is equal to the gradient of the potential f, and so I replace that by gradient, then evaluate what I replaced at point r of t, and then dot it with r prime t dt. This is the formula that comes with the vector line integral. And so we realize that p comes from t equal to a and q comes from t equal to b, so it goes from a to b over there. Now the next thing to notice in here is this this part looks exactly like chain rule, and so that's the chain rule for the derivative of f of r of t. And so that's again this piece is exactly that by chain rule. So replacing that, now I end up with, by fundamental theorem of calculus, I end up with basically antiderivative of what, because it's antiderivative of derivative. By fundamental theorem of calculus, I end up with the one that the antiderivative evaluated at a and b, evaluated at b minus antiderivative evaluated at a, and so that's what we get next, which we just earlier there we actually defined or said that a is the t value that r evaluated at a is equal to b, and b is the value that r evaluated at b is equal to q. So what we have, if I plug in b and a into the function, then the inside would be p and q, and so it's f of q minus f of p.